Let's talk about a very important topic called stacks and queues. Stacks and queues is one of the most important topic when it comes to computers programming. Recursion, for example, is based on stacks. Understanding stacks enables you to better understand how recursion works internally, and hence you can use it to optimize space of your program as well. It's extremely important for interviews. You can expect direct questions on stacks or queues. For example, if you want to find the maximum area under a histogram, you can do it using stack. The parentheses problem as well can be solved using stack. The sliding window problem can be solved using a queue. So these are important from an interview perspective. But having said that, it's also important for day-to-day activities as well. Why? You might have heard about Kafka or Redis queues. These are nothing but the data structure queue, right? At a massive distributed scale. So these are not just important in terms of an interview, these are also important in day-to-day activities as well. Hence, do not skip these topics.
Okay, so today we are going to cover stacks. So let me give you first a little introduction about stack. So first of all, the stack is very much important. It's the most favorite topic of the interviewers. Be well versed with this topic. Like first go through the basics, understand it because they're very straightforward, and then attempt as many questions as you can. There are some standard problems that you should definitely attempt. That was the gist about stacks. Now let's get started. Cool. So stack is very much similar to the stack of objects you see around yourself. So be it stack of plates, stack of books, so stack of plates, stack of books, then stack of, let's say, bowls. So you see it and use it every day, right? So let me draw the stack of plates. So this is how a stack of plates look like. Now from the stack of plate, you can insert a plate only from this end, that is top, right? You can only insert a plate on top, and you can only remove a plate from top. You cannot insert or remove a plate from in between, because that will disturb all the plates, right? So you cannot do that. You can only remove and insert a plate only from top. So that's essentially the idea behind stack, that we can only insert an item from top and we can only remove an item from top. Okay, so conceptually or logically, you can think of a stack like this, where one end is open and three ends are closed. So from only this end, we are going to perform operations, that is to remove an item and to insert an item. As I was saying, that we can only insert an element from one end and remove an element from that end only, and therefore stack is known as lifo data structure. That is the last, as you can see the stack of plates over here. So this plate which was inserted at the very end will be the first one to come out. That is last in, first out. Okay, cool. So first what we are going to do, we are going to understand stack as an abstract data structure, that is ADT, abstract data structure. What do we mean by abstract data structure? In which the implementation details are hidden, but the operations are given to us. Okay, so let me write it over here, that implementation hidden. Okay, it's not there, it's not given, but only the operations are there. Only the operations are there with which, using which we can use the stack. Okay, so for example, you can see the fan on top of you, right? So you don't know how it's working internally. All you care about its operation, as in you put down the switch and it turns on, and you put off the switch and it turns off. That's what you care about. So that's an abstract. Cool. So we are given, let us understand the basic operations that are available with stack. Okay, so there are 4 basic operations. The first one, I am sure you guys, if you know about stack, you must know about all these operations. So that is push function, and then second is pop, the third is top, and the fourth is empty. Okay, so the push operation actually helps us to push an element on the top of stack. So this pushes an element on top of stack. Then here we have pop. So pop removes an element from top of stack. Then we have top, so it returns the element present on top of stack. So whatever element is present on top of stack, it just simply returns it. Okay, so don't worry, we are going to see an example over here. Is empty is the function that tells us if the stack is empty. So if the stack is empty, it returns true, else it returns false. Okay, so these are the four operations, that is push, pop, top, and is empty. Push pushes an element on top of stack, pop removes an element from top of stack, top tells what is on top of stack, and is empty returns true if stack is empty, else it returns false. Remember that pop simply removes an element and top does not remove an element. It simply tells what is present on top of stack. Is it clear now? Okay, so basically while performing a question, you will have to use in C++, let's say you can use STL, right? In STL you have stack. So in C++, you declare a stack like this. You can use a stack like this, and on this object basically you can call all these functions. So push x, then s.pop, and so on. Likewise in Java, you have collections using which you can use stack. So while attempting a question, you don't have to implement a stack of your own until and unless told. Okay, so but in a while we are also going to see how to implement a stack. We are going to actually implement these operations. Okay, cool. Okay, so let's actually see a dry run of these functions. So here this is a stack, and these are the operations that I would want to perform: push 2, push 1, push -1, push 5, then pop, pop is empty, top. So let's perform these functions, okay? So it's push 2. So what we'll do, from where we'll put it from here. So basically 2 will come over here. Then it's push 1. So 1 will come over here. Then -1, -1 will come over here. Then there is 5, 5 will come over here. Then we are popping. So 5 will be gone, right? 5 will be gone. So we have removed 5. Now again pop is there. So -1 will be gone. So we have removed -1. Okay. Then we are checking, is the stack empty? What will it return? What will this return? It will return false because the stack is not empty, right? The stack is not empty. Okay, so now there is top. So what will be the top function return? It will return whatever is present on top of stack. So basically top is pointing over here. So whatever is on top of stack, it will return that. So it will return 1, right? It will return 1. So that was a simple dry run of how can we use these operations. Okay, how these operations work. Now let us come to the applications of stack, which are very important. Applications of stack. So some of the applications are undo, redo. Then we have arithmetic expression, evaluation, right? Then we have recursion. So these are some of the, then we have string reversal and so on. So these are some of the applications of stack which are very important and you must know. So try to figure out that how a stack can be used in these operations. You know, that's an activity for you, that do try to search that how we can perform an undo, redo. So this is actually present in your browser, right? So whenever you go to any page, from any page, and want to come back, so basically you store, for example, let me give you an example. So you are at link, let's say 1, then you go to link 2, then you go to link 3, and you want to come back to link 2. So what you can do, you can actually maintain a stack of them. So like first you are on link 1, you can put it on a stack, link 1. Then you are going to link 2. So put it on top of stack. Then you are going to link 3. Then put it on top of stack. Now you want to come back to link 2. So what you can do, you can simply remove this. And now you are back to link 2. Does that make sense? So likewise, you can also have a redo stack. Okay, so that's an activity for you, that how you can perform a redo operation. Okay, so likewise try to figure out. And we have arithmetic expression evaluation. So I think you all must be very much familiar with this. That is, converting to infix to prefix or postfix, then evaluating the postfix notation. So that's where you can use stacks. Okay, and then you have recursion. Stack is a core of recursion. So you make function calls, and when you come back, so that basically those function calls get stored on top of stack. Okay, likewise string reversal. Okay, so there is another application that you may be using in your daily life. You must have seen this InShots app, right? So what happens in this, you are on this screen, okay, and so here I am actually at my feed. I am at my feed, okay, and I am watching this news. So I can only see another news if I remove it, if I remove this. So can you see that how this is an implementation of stack, right guys? Now let's talk about the implementation of stack. So could you guys tell me how can we implement a stack? So using arrays, second is using linked list. Okay, so how can we implement a stack using arrays? So basically, let's see. So we can have an array. So size of the array is, so array is A, and size of the array is 7. Okay, so what we can do, so let's say I want to push 2, push 3, push -1, pop, push 7, pop. Let's see how can we implement these operations using stack. Okay, so what we can do, basically we can actually enforce that one end of the stack will be there to perform all the operation. So you can imagine it like we are pushing the elements from here and removing the elements from here. So let's say I want to push 2, so 2 comes over here. Now you can also maintain a top variable which is right now pointing over here. That means what is on top of stack? 2 is on top of stack. Then we have push 3. So what we can do? We can simply increment this top variable and push 3 in here. Then push -1. So we can simply increment this top variable and push -1. Now how to pop it? How can we pop it? Top minus minus. So basically we are now at index 1 and we have, so basically -1 is gone. Okay. Then we are at, so this was done, then we are at 7. So again we can increment the value of top and 7 comes over here. Now again pop's coming. So we can come over here and this is gone. So basically that's how we can operate a stack using arrays. Okay. And now can someone tell me the problem of stacks? So problems of stack are, which are very important if let's say an interviewer asks you to implement a stack using arrays or linked list. So if I talk about arrays, then we have problems, overflow and underflow. Let's say I want to push 1, 4, 0, 5, 6. These are the items that I would want to push. So 1 comes over here, then 4 comes over here, then 0 comes, then 5 comes, then 6 comes, and now I would also want to insert, let's say, -1. So as you can see, as I move my pointer forward, there is no space because array has a fixed space, right? So I cannot insert any more element, and that leads to the condition of overflow. Okay, and it's very important. So if interviewer has asked you, he's basically maybe judging you that will you cover these cases or not. Okay, so this is the thing. So how can you handle it? So basically here you have mentioned a size, right? You can keep a check that if size, so if top is equal to the size -1, so in that case, that's an overflow. You cannot insert any more elements. So that's a drawback of arrays. And to overcome that, basically, you can use something known as dynamic arrays. Okay, you can use something known as dynamic arrays. Okay, now let's say I want to pop, I'm calling pop 7 times. Okay, so basically this is gone, third time, fourth time, fifth time, sixth time, and seventh time, and now I am again calling. So now what will happen? Will I be able to pop any more element? No, I will not be able to pop any more element because the stack is empty. So if I attempt to do so, that will lead to underflow condition. So how can you make it all right? Basically, you can put a check that if top, so if top is equal to, let's say, -1, then print underflow, okay, and simply return. So that's how you can manage underflow and overflow condition. Does that make sense, guys? Underflow is when you are trying to pop an element when there doesn't exist. When you are popping an element when there is no element. So how will you be able to pop? Will you be able to pop? No, right? So that's the case of underflow. So you can manage the case of underflow by checking that if top is equal to -1, that means you have no element. So you simply print underflow and return. Cool. So let's talk about linked list. So in linked list, what you can do is, so you have nodes in linked list where this is the data part and this is the address part. So basically, the nodes of the linked list can be present anywhere in the memory, right? Like array, you don't have everything in a contiguous manner. Everything is scattered. Every node is scattered in linked list. Basically, if you have this as a memory, so if let's say one node is present over here, another node can be present over here. Okay, third node can be present over here. So basically, this address field actually links node. So basically, this will be linked to, let's say, this, then this is getting linked to this, and so on. That's how we store data in linked list. So basically, let's say you have 2 and 1 right now. Then you want to insert, you want to push, let's say, 7. So how you can do? Right now, top is here. So at what position, if you, so you are actually, remember, you are actually implementing stack using linked list. Where would you want to insert this node? This is your linked list. This is what you are building. This is the temp node, current node, that you new node that you want to insert into your linked list. So where will you insert it? That we can actually put it on top of head. So now we can actually make this its next pointer point over here. So this is how our stack would look like. Now top will be over here. Okay? So you can, in case of a linked list, you can imagine a stack like this. Like this, it's growing, right? Like this is it's growing. And when you want to pop an element, so basically you can actually shift this top to the next position, and this will be, so basically you can free up this space. Okay? So that's how you can implement a stack using linked list. Now with linked list, the concept of space. A lot of space is used in linked list. Okay, so basically you are storing pointers as well. That will take a lot of space. And pros of both stack and cons is that you will be able to perform push and pop operation in just order of one time complexity. Okay, in just order of one time complexity. Okay, cool. Let's get to the question. Okay, so the first question that we have is of Very much famous question and very much asked question. It's of valid parenthesis. Okay, valid parenthesis. So the question says that you are given brackets, the round brackets, okay, and you have to tell whether the parentheses are balanced or not. Let's say you are building this compiler in which you will be writing your code, right? So basically you will be you want your compiler to check, verify your code. So in that case you will definitely want how can we check if the bracket are valid or not. So how can we do that? Let's see. First of all, let me give you some examples. Let me write down the examples. Okay, so what do you say about the very first parenthesis? What do you say about the very first parenthesis? Are these set balanced? Is it balanced? Yes, it is balanced because a corresponding opening bracket has a corresponding closing bracket. So yes, it's balanced. Then if I talk about this, is it balanced? No, it's not, because this is complete, they are balanced, but here this opening parenthesis is lacking a closing parenthesis, or you can also say that this parenthesis is lacking a closing parenthesis. So this is not balanced. This is not balanced. Likewise for this, so this is lacking an opening bracket, or you can also say that this is lacking an opening bracket. So this is also not balanced. Okay, so you have to basically tell, are the parentheses balanced or not? Let's say we want to attempt this question without star. Can anyone think of something? Okay, so let me first actually put some observations. Let's do the question step by step. Okay, let's do the question step by step. So observations are, the first observation is that, can an opening bracket make a string invalid? As in, let's say I'm traversing the string and I find an opening bracket. So can that opening bracket make the string invalid? Well, it depends upon the future. It depends upon the future, that if I have this opening bracket, maybe in future I'll find a closing bracket and that will be valid. Or let's say I don't find a corresponding closing bracket, in that case it will be invalid. So it totally depends. It totally depends if I get an opening bracket. Okay. Now if I talk about a closing bracket, so what about a closing bracket? Can a closing bracket be a problem to us if we encounter it? Well, so if till now for a closing bracket there was no opening bracket, in that case, yes, it is a problem, because even if we move any further, the string that is given to us will not be valid in any case, right? In any case. So basically, let's actually okay, let's take look at it like this. So I have something like this. So what will happen? Let it be like this. So I am at here. I will maintain, what I can do, I can maintain a left and right count which can be initialized to 0. Now I am at an opening bracket. So that means left actually tells a opening bracket and right tells the count of a closing bracket. So I found an opening bracket. This becomes 1. And so let this be the thing. Let this be the bracket. Now I am here. Now I am here. So what I can do? I can simply decrement the value of this, and that will tell us that we actually found a match for an opening bracket. We actually found a match for an opening bracket. So we can actually set this to 0. Right. Now let's say I have a string like this. What will happen? What will happen? That I am here, left and right. So basically I have left 1, then I have a closing bracket. So initially both are 0. So now this is a closing bracket. So is left greater than 0? Yes, it is. That means there is an opening bracket. So we can simply decrement it, telling that we have found a match. Now next we go to the next character. This is a closing bracket. Okay. So what's the value of left? It's 0. That means there's no opening bracket. In that case, we will simply return that it's invalid, because at this point there is no use to move any forward, because this closing bracket does not have a matching opening bracket. So we can simply return from here. Does that make sense to everyone? Okay, so whosoever is saying that can we count the number of opening bracket and the closing bracket? Guys, we cannot simply count the number of closing bracket or opening bracket. Okay, let's take an example of that. Let's say I have this as a string. So now left is equal to 2, right is equal to 2. But are they valid? Are they valid? No, they are not valid because they are not placed in the correct order. Therefore, this is not a right approach. Is that cool? The time complexity of the approach is what? What's the time complexity of the approach? So if we have this case, here the number of opening brackets, closing brackets are 2, number of opening brackets are 2. So are they valid? No, they are not valid. So this is wrong. This way is wrong. So what's the time complexity, guys? Time complexity is just order of length of the string because we are iterating the string just once. And what's the space complexity? Just order of 1. We have not used any space. Okay? We have not used any space. Now, let me make a question little trickier. Now, let's say I have brackets these and these. So, this is an extension of the question. Extension hai ye question ka. Now, I am saying that I have these 3 sets of parentheses. Now, I have to tell. Basically, my string can contain these set. So, I have to tell if those are valid or not. Let's take an example. Examples can be this, then we have this. So this will be given to you. Now you have to tell are they valid or not. Now how can you do it? How can you do it? So whenever in the interview you're telling the interviewer that okay, we can use stack for this, but she or he already knows, right? You have to get to it. Like how? What's the intuition? So that's is very important. Okay. Some of you are saying that we can use 3 variables. So that will be wrong because then you won't be able to actually find the order. You cannot judge the order by taking that many variables. So first of all, I am sure that you guys understand that it cannot happen by taking just the left count and the right count, because okay, so first of all, let's take the example of this. Now here left is 1, okay, and now I find a closing bracket, but here they are not same, right? So this will not work. Having left and right is a bad idea. Now taking 3 variables. So here I have this string. So if I take 3 variables, let's say round, or let me write first bracket, second bracket, third bracket. Now here the first type. So this is type 1, type 2, type 3. First bracket ka left, right, iska left, right, then iska left, right. First ka left is 1, okay. Third ka left is 1, okay. First ka right. So we have found a right bracket and this manages to be 0. Then we have third ka right. So this becomes 0. But is this valid? No, it's not valid because the order is different. Order doesn't match. So therefore, that's a bad choice. Does that make sense? You should have a clear idea that why your approach is wrong. You should take as many, like if you are stuck, you are not able to think, take examples and try to generalize it. You guys are clear with it? Cool. So let's move forward. Now let's actually build some intuition of this. So one thing is that, let's consider these brackets. One thing is that okay, so this is invalid, right? This is invalid. This is also invalid, right? This is also invalid. This is valid. This is valid. They have right set of pairs. Now this is also, this is what? This is what? This is also valid. Okay. This is also, as you can see, that this is also valid. So if I talk about this string, then it's a property of the valid parenthesis that if the complete parentheses are balanced, then their sub parentheses will also be balanced. as you can see that this is balanced, this is also balanced, this is also balanced. So we are not considering all the substrings, right? We cannot consider anything like this or something. We have to choose the right set. But what it means is that whatever the parentheses are inside it, they will be balanced anyhow. So this is its corresponding pair. Then we have this, it's correct, then it's correct, then this is there. So does that make sense? That inside of it parentheses are balanced? Now, so an opening bracket does not bother us, right? An opening bracket does not bother us because in future we may find a closing bracket for it, right? But let's suppose I am at this closing bracket. Let's suppose I am done with everything and I am at this closing bracket. Now for this closing bracket, this is an opening bracket, this is an opening bracket. Does these brackets are of any use to me? No, they are not. Can I get rid of them? Then that would be great, right? So if I can get rid of them because they are valid in itself, right? As I told you by this property. So since they are valid, if I can get rid of them, then I can actually find out if this bracket has a matching opening bracket. Okay. So let's actually see a dry run of this using stack, because stack is the data structure that helps us find. Just look at just the past. Okay, just the past. So how and what we can do? We are at this bracket. This is our opening bracket. We'll see about it in future. So push it onto the stack. Then this is an opening bracket. We'll see about it in future. Put it on top of stack. Again an opening bracket. Put it on top of stack. This is a closing bracket. Was there an opening bracket for this? Yes. Where can I see? I can see it on top of stack. If there is a corresponding match for this closing bracket, then I can simply pop it off. Next time here, this is a closing bracket. Does this have a match? And see how nicely we have removed between whatever was presented. That is here, we have removed it. We have removed it. And now we are actually comparing this. Where can we find it? On top of stack. So yes, it has a match. Remove it. So now we are here. Now we are here. Put it. So this is our closing bracket. Yes, match found. So remove it. Remove it from top of stack. Then we have an opening bracket. Push it on top of stack. Okay. Then we have a closing bracket. Is the corresponding opening bracket present? Yes, it is present. Remove it from top of stack. Now we are at the last bracket. Is the corresponding opening bracket present? See here how we have gotten rid of all of this, right? So basically, yes, it's present. From where we can find? On top of stack. Just remove it. What's the condition we have to check for validity? That if the stack is empty, then return true, right? If the stack is empty, return true. But if the stack is not empty, so we have to return false. That tells, even after iterating the string, let's say we have completely iterated the string, even if the stack is not empty, so we will have to return false, right? Because there are still left some unmatched opening brackets. So at any time, let's say you have something like this. So at any time you don't find, so okay, let's do a dry run of this as well. So this is an opening bracket, move ahead, opening bracket, move ahead, closing bracket, but no corresponding match. Simply return from here. Simply return from here. Okay, so now let's move on to the next question. But before that, let's talk about the time complexity. The time complexity of this approach is just order of n, because we are going to each and every bracket not more than twice. How? Once while pushing it and another time while popping it. So that's only 2 into n, which makes it order of n, right? That makes it order of n. And the space complexity is order of n, because in the worst case, we may end up pushing all the brackets in the stack when, let's say, the string was something like this. In that case, you will end up pushing all the brackets in the stack. So the space complexity is order of n. Okay, so I hope that's clear, and we'll quickly move on to our next question. So intuition is that how can we, previously clear up something to get just the, so here as I talked about that step by step we made the intuition, like, sorry, I just removed it. So as I was talking about that, inside of it will also be balanced. So if we can remove it, I will just be able to look at here. That's what I want to do. So we can simply remove it, and that is possible using stack. Okay, so let's move forward quickly. Cool. So question 2, and this is very, very famous question, which is of next greater element. Okay. So question is that, let's suppose you are given an element, you are given the elements in an array. Let's suppose 10, 13, 22, 7. For each of these elements, you have to tell that what is the next greater element to its right. Just the next greater element to its right. So what's the next greater element to the right of 10? It's 13. Okay, it's 13. The next greater element for 13, it's 22. The next, is there any next greater element for 22? No, it's not. So we can put -1 over here. We can put -1 over here. Then we have 7. So next greater of 7 to right of it, it's -1. Nothing is there. Nothing is there. Okay, so let me take, this was example 1. Let me take another example as well. So we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Okay, so what's the next right to the right of 10? It's 11, right? Just greater element on the right of 10. It's 11. Just greater element on the right of 7. It's 9. It's 9. Just greater element to the right of 4. 9 again. To the right of 2. 9. Just to the right of 9. It's 10. Just to the right of 10. 11. Just to the right of 11. Nothing. To the right of 3. Nothing. To the right of 2. Nothing. Okay? Okay, cool. See, if you are implementing any question, you can use STL in C++ or collections in Java. You don't have to implement push pop functions on your own. That's just for the sake of if let's say your interviewer asks you. That's it. Okay, that's it. Cool. So if the question is clear, please tell me that how can we attempt it. At least give me the brute force approach. At least give me the brute force approach. So you will agree with me that brute force is nothing. So brute force is using 2 loops. So you can basically, let me actually write the code for it as well. So the brute force look like that. You can have an answer variable, answer array. Then you can iterate through all the elements from 0 to n-1. Then for those elements, you can again iterate from. So, okay, first you can initialize your result to -1 if let's say you don't find any element. So you can do for j that goes from I plus 1 to n-1. You can check if a of I is, so a of I is less than a of j, then simply put answer I is equal to aj, okay, and break from here. Take a break from here because you just have to find just the larger element. You don't have to iterate any further. Okay. Now what do you have to do? Actually, this should be result, and out of this for loop, you can set answer I is equal to result. Does that make sense? This is just the brute force approach. Okay, cool. Let's go ahead. So the time complexity of this approach is order of n square, since there are 2 nested for loops, and the space complexity would be order of n, which we can ignore because that will be just to store the, so basically this is just so we can actually make it order of 1 only, because we anyway have to take an answer array. Answer array we anyway have to take because that's how we are going to return the answer. So the space complexity for this we can assume to be order of 1, right? Cool. Now let's talk about the optimized approach and let's build some intuition for that. Let's see some observation. The first observation is that let's suppose the array elements are 12, 10, 9, 8, 7. Okay. 0, 1, 2, 3, 4. If let's suppose these were the elements, what is going to be the answer for them? What's going to be the answer for 12? Minus 1. Nothing is on right. For this, minus 1. For this, minus 1. Minus 1. Minus 1. Does that make sense? The answer for all of them will be minus 1. Now let's talk about another example. Let's say we have 5, 4, 3, 2 and 10. Now can someone tell me what is going to be the answer for 5 now? For 5 it's going to be 10. For 4 it's going to be 10. 3, 10, 2, 10, 10 minus 1. Does that make sense, guys? Cool. So the thing is that as you can see, when the sequence was in decreasing order, we got minus 1 for them. And here we also had a sequence in decreasing order. But once we got an element which was greater than them, so this element was greater than these elements, so the answer for them became 10. The answer for them became 10. Look at it like this. So let's suppose I have a 5, 4, 3, 2, 10. So I start from here. This is 5, then this is 4, this is 3, this is 2. Now 10 came. So once the number came which was out of order and greater than them, so answer for them became 10. Okay, answer for them became 10. Let's look at one more example. We have 9, 6, 5, 4, 8. So this is 9, this is 6, this is 5, 4, then 8 came. So 8 is 8 to whichever element it is greater, it will become the answer to them. That is here. So this is 9, this is 6, this is 5, this is 4, this is 8. So 8 will become the answer for 6, 5 and 4. Okay? So basically now once we have got the answer for them, can I just ignore this and start by finding the answer for these now? Does that make sense? Does that make sense? Okay, giving you some intuition that here we are also ignoring whatever was redundant from the past. The idea here is that we have a monotonic sequence. We have a monotonic sequence over here. Monotonic sequence is when we have a decreasing or increasing sequence. So my point is that I had a decreasing sequence. Once I find an element out of order, so all the elements which are smaller to this will be the answer for them. This will be the answer for them. Okay? Now, so basically, let's say I have elements 11, 4, 3, 2, 10, 12. So I have 11, then I have 4, then I have 3, 2, 11, 4, 3, 2. Now 10 comes. Now 10 comes. So 10 is greater than these numbers. So answer for these will be 10. Answer for these will be 10. Now since we have got the answer for them, we can actually remove this. We can actually remove this, and now it will become such a sequence. It will become such a sequence. Now 12 comes. So this will come over here. Now whatever is smaller than answer to them, 12 will become the answer. So 12 will come over here and 12 will come over here. Now only. So we have got the answer for them. So we will remove it. And now we are just left with 12. We have completely iterated the array, and whatever we are left with, to them the answer will be minus 1. Minus 1. Okay. So since we are ignoring whatever is redundant to us previously, and since this is a monotonic sequence, therefore stack will help us over here. So let's see the dry run using stack. So intuition was that we had to look at the just past, removing this just past. So whatever answer we had got, we will just ignore them, and now we'll start again from some monotonic sequence like we did over here, over above, right? Okay, so now let us go through the dry run using stack. Then again, if you guys will have some doubt, we will come to those. Okay, so I have 11, put it onto the stack. So 11 has been put onto the stack. Then we have 4, put it onto the stack. Then we have 3, put it on top of stack. Then we have 2, put it on top of stack. Then we have 10. Now this, you can see that this is a decreasing order. This is a decreasing order. Now we found an element out of order. So to whatever elements 10 is greater, the answer for them will become 10. So is 10 greater than 2? Yes. So we found the answer for 2. Answer for 2 is 10. Remove it. Is 10 greater than 3? Yes. We found the answer for 3. The answer for 3 becomes 10. Remove it. Now is 10 greater than 4? Yes. So we found the answer for 4. The answer for 4 becomes 10 and simply remove it. Now is 10 greater than 11? No. So simply push 10 onto the top of stack and move ahead Now we are at 12. So on top of stack there is 10. 10 is lesser than 12. So answer for 10 will become 12, right? Answer for 10 will become 12. Now, so we are at 12. Is 12 greater than 11? Yes. So answer for 11 becomes 12. Okay? So now nothing is there. Simply insert 12 on top of stack. Now move ahead. So we are done. We are left with no more elements. So whatever is present on top of stack, the answer for them will become -1. So in this case, answer for 12 is -1. Guys, does that make sense? So Anshul says that then in this solution, we need to also store index and stack. Anshul, that's what we are going to do. We actually need to store indexes on top of stack because we actually are trying to find the answer for the previous elements that we are done with. So let me quickly show you a dry run of how we can do this using indexes. Okay. So we are having the stack. We will place 0 over here. Then we will place 1, right? Then we will place 2. Then we will place 3. So basically still the array is in decreasing order. Now we found 10. So this 10 is greater than what is present on top of stack. So basically answer for this. So we will write it like this. S dot top. Okay? Because this is the index. So a of 3 is nothing but 2. So 10 is greater than 2. Answer for this has become 10. Then likewise, answer for this will become 10. Element at index 1 is 4, which is lesser than 10. Answer for this becomes 10. Now 11 is not smaller than 10. So we will simply push the index of 10, which is 4. Then we are here. Now this is 12. 12 is greater than a of s dot top. So we will simply mark the answer of a of 4 as 12. So this is 12. Again, so as we remove it, then a of 0 is lesser than 12. Answer for a of 0, that is 11, will be 12. And now whatever is present on stack, whatever is present in stack, you will simply mark their answer as -1. So you will put -1 here. And the time complexity of this approach is order of n. Since we are putting an element and removing an element just twice, so again order of 2 into n, which is nothing but n. And space complexity in the worst case can be, when let's say the complete array is in decreasing order, it will be order of n. So does that make sense to everyone? Okay guys, so we have actually placed the link to the questions for the next questions. Okay, so hope you guys try it, and guys, this was it. I hope you enjoyed it. Cool. Please try them. See ya. Bye-bye.
Hey everyone, in this lesson we will discuss logical view or abstract view of queue data structure. Basically, when we talk about abstraction, we don't go over implementation details. We generally discuss about features and operations. In actual practice, queue is a structure in which whatever goes in first comes out first. So in general, queue is a FIFO structure. Whatever goes first, it should goes out first. So if we want to construct queue as a data structure, then we need to support both insertion as well as deletion in the queue. In queue, as we need to maintain FIFO property, so both removal as well as insertion should happen from different end. It means if insertion happens in the front, then deletion should happen from the end and vice versa. Let's take an example to understand this thing. Let's say this is the snapshot of the queue at some particular time. Let's say this is the snapshot of the queue. and this is the front element of the queue, and this is the last element of the queue, or we can say as rear element of the queue. Now, so as we can see here that if we want to make an insertion, it should happen at the end of the queue, which we call as the rear or tail of the queue. Likewise, deletion should happen from the start of the queue, which we call front of the queue. As if I want to delete some element, it should be even because this element entered first into the queue. And if I want to insert some element, it should insert here. So this is the snapshot of a queue at some particular time. Okay, so what we have seen here, queue as a abstract data structure, a list or collection with the restriction that insertion can be performed at one end, that is the rear of the queue, and deletion can be performed at other end, that we can say here as the front of the queue. Let's discuss operations in the queue now. If we want to create a queue, what sort of operations that we need to support? The first operation is insertion, which we call enqueue in the terms of a queue, or we can also say it as push operation. We need to push an element into the queue. And also one other operation that we need to support, that is the dequeue, where we need to remove one element from the queue or pop an element from the queue. Now, if I want to create an interface for the queue, how it will be like? Let's discuss about that. If I want to create an interface for the queue, it will be something like I need to support these functions. The first function is enqueue, which supports insertion. And the second operation is dequeue. And here I am assuming that queue is maintaining integer elements, but it can be of any type. Okay, and the dequeue operation means delete an element from the queue, and where this return type symbolizes the element that I deleted. It solely depends upon the implementation that whether we want to return that element or not. We can keep it as void as well. That depends upon the implementation. Also, what sort of other things that we may need from the queue. That what is the element which is present at the front, or we can say it as peak. Is my queue empty or not? So these sort of operations that I may need in order to implement a queue. So what we can say that in high level terms, these sort of operations that we need to figure out in order to implement queue. And most of the languages has an inbuilt library which provides the interface, which may vary from language to language. And as a developer, we don't need to worry about the implementation details, and we can create a queue data structures with the help of available functions. As we have seen here that the operations can be enqueue, dequeue, front is empty. Now what we can say also as queue as a container which is open from both ends. As we have seen here that we are entering an element from this side and removing an element from this side. So it is actually an open container where element goes in from one end and element removes from other end. Now let's say we have this operation available in the library. Let's try to simulate queue. Okay, let's say in the starting we have an empty queue and we need to insert an element 2 into the queue. That means as we have in library, so then we can simply call enqueue function of that library and we can insert 2 in our queue. So when we insert 2, it will come from here. Fine. So now as we know that we need to maintain 2 pointers or 2 variables which keeps track of which is my front element as well as which is my rear element, so that the implementation becomes easy. But so if we have only one element in the queue, then both front and rear pointing to 2. Fine. Now let's say we are inserting one more element into the queue, that is 5, and it will go from the rear side, from this side. Now we need to update our front and rear. Let's say internally the library, it's handling all those things. Now the rear reaches here and front remains here. Now let's say we have one more operation. Let's say somebody asks one more operation to insert 3 into the queue. Then the snapshot of the queue will be something like this, where the rear is pointing here and front is pointing here. Now let's say somebody asked us to dequeue an element, that means delete an element. As we know that deletion occurs from other end, from this opening of the container. So then our front got updated to 5 and the rear will be 3. So now we have done the simulation part and we have seen and the queue in a high level way actually. Now let's discuss some real world examples to understand it better. And it is generally used when there is a shared resource that's supposed to serve some request, and resource can handle one request at one time. In such scenarios, it makes more sense to queue up the request and the request that comes first serves first. Let's consider an example. Let's say we have a printer that is being shared across the network and it can print only one document at a time. When more than one request comes to it, it cannot say that I cannot serve your request. So what printer will do? It will maintain a queue of requests and serves them one by one as long as there is a request in a queue. It will keep picking up the request one by one. Let's say we have a printer and all these computers, they are requesting to the printer for the request to print a document, but the printer can only print one document at a time. So what the printer will do, it will maintain a queue and store all the requests into the queue. And what it will do now, after serving a request, it will pick an element from the front of the queue and serve that request. In this way, it will manage everything. So this is one of the real world scenario where we can use queue. This is good for the introduction part of the queue. In the next lesson, we will see how we can implement queue. Thanks. Hey everyone, as you can see here that we have already maintained the 8-day streak and we need to maintain a streak. So in today's class, I think we will solve some of the questions of stack and queues. Let's proceed at that level. Let's solve some questions. Okay, let's solve the very first question. The question is, let's say all three questions of this clever stack. Okay, let's start the question. We have been given an array and in that array, we need to find the nearest smaller element gi for every element ai in the array such that the element has an index smaller than I. Okay, let's say we have more boundary, gi is the element aj is greater than I. Okay, the basic question is for each particular element in the array, we need to figure out the nearest smaller element for that particular element in the array. Okay, let's say this is our array. And for 4, as we can see that no element is less than 4 in the left side. So we have g1 is equal to -1. So for 5, as we can see that the minimum most element for 5 in the left side is 4. So our answer will be 4 for this case. Now if I can see for 2, okay, both 4 and 5 are greater than 2. So for 2 as well, I can see that there is no minimum element in the left hand side. So -1 will be for this as well. Now, okay, similarly, okay, now let's try to solve this question. Okay, how I can solve this question? Let's first think. Okay, for each element, if I do in a brute force way, what I need to do, I will just iterate over all the elements in the left hand side and I just figured out whether there is an element which is lesser than that particular element. If I figure out that element, then I found the answer. In that way, I can proceed. Let's first copy this example. Okay, okay. Now what we can do, how we can solve this question, let's see. Okay, let's say, let's start from the end. Fine. Okay, let's say in the initially we have an element 8 only. Okay, now as I move ahead, I just found an element 10 and I know that that element is greater than that element. So I haven't find the answer for 8 as well as 10 yet. So what I can do? Okay, now I just figured out 2. Okay, one thing that is clear to me that 2 is smaller than 8 as well as 10. So, okay, so one thing for sure that I can say that 2 will be the answer for both 8 and 10. Okay, so what I can do, I can update my answers and I just need this data point only because I already figured out the answer for this. So I just need to maintain 2 only. Now let's say I just go into the other element. I have 5. Okay, if I found 5, When I have 2 to which I need to figure out the answer, for 2, I know that 5 won't be the answer. So I haven't found the answer for 2 as well as 5. Now I figured out 4. Now I figured out 4. I can say that, okay, 4 is lesser than 5. So for 5, 4 definitely will be the answer. For sure. But for 2, it won't be the answer. So after then, I need to store these 2 points. Isn't it? So the way if I will do in that way, I will figure out the answer. So what I just think, okay, I am appending the elements, and as I'm appending the elements, I'm checking. And if I need to check the element, what I'm doing, I am just first checking for the last element and then the second last element, and I'm doing in that way, and I'm able to solve this question. If I'm able to do in that way, then it's easy to solve. So I need some sort of data structure which helps me to maintain this information. And that data structure should be something like where I can add the element in the end such that I can also remove the element which I just added in the end. So it should be last in, last out. And we know that stack is that data structure which provides that sort of thing. So I can use stack here and just try to solve in that way. I am able to achieve, because what I am doing, I am adding an element in the stack, and when I just found an element which is lesser, what I am doing, I am just checking with all the elements in this stack, and if I figured out an element which is greater than that element, I'm just removing it to the stack. So only I am adding an element one time into this stack, and I also am removing from this stack only one time. So that means it's kind of order of an algorithm that we just achieved. Okay, let's try to think how we can write code for this question. Okay, let's write the code. Okay, let's try to think what are the constraints that we have been given. Okay, we have not been given any constraint, and the thing is, if we haven't find an answer for any element, we need to return -1 for that particular case. Okay, let me first, what I can do, let me first figure out the size. Okay, let me create my answer, which is of size n, and let me have the default value as -1 for each particular element in that particular array, because we haven't find the answer, and we will follow the algorithm as I discussed here so that we will be able to achieve our solution in order of n time. Okay, let's try to think, okay, how I can do that. We just need to iterate. In the last element, I need to move till the first element. In that way, I need a stack data structure to maintain the information as I just discussed. Why? Okay, so now what I can do if I need to question, okay, one thing I need to be sure that, but what will be the edge case? If my stack is empty, or if I have my element which is at the top of my stack, okay, if I figured out an element, okay, which is greater than my top, then that means I haven't found the answer for both of the elements. So I need this data. So I need to push that element into my stack. If that is the case, if that is greater than, that is element is greater than or equal to my that element, so I need to push that element into my stack. Isn't it? Okay, now I'm done here. So I can new. Okay, if there is other case, if the element at my top is greater than AI, if that is the case, then I need to check for how many elements I have found the answer. So let's first just check the edge case, whether my stack is empty or not. While my stack is not empty and my top element in the stack is greater than AI, in that case, what I can do, I know that answer for stack dot top will be equal to AI for sure. I know. And I can safely remove that element because I just figured out the answer for the topmost element in this stack. Now I need not need this data in the future. So I can safely remove it. By the time this thing gets ended, I can say that, okay, now I'm done. Now I can safely add a ith element because I haven't found the answer for ith element yet. And in the end, what I can do, I can return my answer. And let's check once again whether I'm doing in the right direction or not. I am maintaining my answer, and I just created an empty stack, and I'm checking if my stack is empty or if it is greater. So then I need to push that element into this because it's of no use. Otherwise, I need to check if my element is lesser. So that means for that first element, I just figured out the answer. So what I need to do, okay, in that way, if I just do in that fashion, I can solve. Okay, that seems like a good approach. Let me test. Okay, it's giving me correct answer. So let's submit. Oh, nice. Nice. We have solved this question. Now let's move to the next question. Okay. What will be my next question? Okay, now the next question is I need to figure out the largest rectangle in the histogram. Okay, that is my question. Let me think. Okay, let me first read the question. We have been given an array of integers a of size n where a represents a histogram. That is, ai denotes height of ith histogram bar and width of each bar is 1. Okay, let's say we have been given this histogram and where the height of first bar is 2 and the height of second bar is 1 and height of third bar is 5 and fourth bar is 6 and so on. And above is histogram and width of each bar is 1. And we have been given heights like that and we need to figure out the largest rectangle in that histogram. Okay, let me think how we can figure out that thing. Okay, if that is the case, this will be my answer. Okay, they are saying this is my answer, and the answer will be 5 as my height and 2 as my width. So my answer for this will be 10. Okay, so let me just copy this thing. Let's try to think how I can solve this question. Okay, so the question was we have been given an histogram where the values are 2, 1, 5, 6, 2, 3. Okay, and we have been given histogram like that. Let me first draw the histogram on the paper and then it's more suitable. Okay, 1, 5. Okay, it will be 5 and then 6 and then 2 and then something 3. Fine. So this will be my answer in this case. So what I can think is what can be the brute force way to solve this question. One thing is coming to my mind. I can solve it in a way that okay, let me take all the contiguous segment to solve this question. Okay, and I can take all the contiguous segment of length 1, then length 2, and just try to find the answer for that contiguous segment. Let's say I just take this contiguous segment of first three element, which is 2, 1, and 5. What will be my answer for this contiguous segment? Okay, I know that the width will be equal to 3, but what will be my height in this case? Okay, I can surely say that if I want to build a rectangle, then the height will be the minimum height histogram available in that contiguous length, isn't it? So I can say that the height will be 1. If I do in that way, then I can solve this question. That is fine. Okay, so if I just take in a brute force way, so how much time it will take to me? I need to iterate over every contiguous segment, and to iterate over each contiguous segment I need to take two variables L and R, so it will take order of n square time, and for each contiguous segment I need to find the minimum most element. So the complexity will go up to n cube. So it doesn't sound me a good solution to solve this question. Can I think something else to make my algorithm better? Okay, let's think what I can do. Okay, let's think. Let's say I have an example, something like this. Okay, let's say this is my example. If I build a histogram, I have 7 here and I have 8. I have something 6. I have again 8 and I have something again like 7. Okay, if I am just considering all the contiguous segment, I will consider this segment as well, and I will consider this segment as well. I will consider this segment as well. I will definitely consider all the segments. If that is the case, that means, but I know that for all these segments, if I did in that segment, 6 is the part of that segment, then my minimum value will always be 6. Okay, can I use this idea to achieve something? Okay, why I am just iterating over all the contiguous segment? Why not that maximum contiguous segment for 6, which will give me the answer? Because in any way, other contiguous segments are waste for me. That's the waste of computation time. If somehow I just figured out for that particular 6, what will be the maximum contiguous segment if I just consider this element? So one thing I can surely say that, okay, if I just consider this element, how much elements I need to take in the right hand side, that I need to consider. Okay, I can consider 8, I can consider 7, but if I have something 5 here, I can't consider that element. Okay, this gives me the idea that what I can do, I can just take the nearest minimum element for a particular element in the right side. Fine, because such that all the elements in between will be greater than 6, and I can consider those elements for this element. And likewise, I can extend my similar approach in the left side as well. So this gives me some idea. If I do in that way, I can solve my problem. Okay, so this gives me the idea what I need to do for each element. For each element, I need to figure out the nearest minimum element in the right hand side as well as in the left hand side. Because I can surely say that this will be the maximum contiguous length for that particular element, which will give me the answers. And if I take any smaller contiguous length for that particular element, they are of no use. And in the previous question, we just solved how to figure out the nearest minimum element for any particular element. And we know that we can solve this using stack in order of n time. We just solved it. Okay, I can use that approach here as well, and I can solve this. And I can solve similar for the right hand side and for the left hand side, and I'm done. That is sounds like a good solution. Let's write the code for this now. Okay, let's write the code for this question. Now let's say this is the case. Let's first try to dry run this. Okay, now for 2, I know that the nearest minimum element for 2 in the right hand side is 1, and in the left hand side I don't have any element. Fine, and so I just end up with the contiguous segment of one element only for 2. So that means for 2 my answer will be just 2. Now if I take 1, now for 1 I can see that for 1 5 is greater, 6 is greater, 2 is greater, 3 is greater. So I can pick all the elements for 1 in the right hand side. That is good. And in the left hand side as well, I can pick all the elements. That sounds like a good thing. So I can do like that. If I do in that way, so for 1, length available will be equal to n. So which is 1, 2, 3, 4, 5, 6 in this case. So my answer will be 6. Now for 5, if I do in similar way, I can see that for 5, the minimum length available, 6 is greater than 5. And okay, I found element 2 which is less than 5. So I can only consider these 2 elements for 5. Now if I just think of an element in the left hand side, I can see that 1 is the minimum element for 5. So I can consider only these 2 elements for 5. So I have a length of 2 for 5. I have a length of 5. So my answer will be 10 if I take 5 as a length. Okay, now if I take 6 as a length, then my area to consider for 6 will be, I can't take this element because this is smaller than 6, and I can't even take this element. So because these 2 elements are the nearest minimum element for 6. So I just have a one length for 6. So my answer will be equal to 6 only. Okay, now I consider for 2. If I want to consider for 2, okay, 3 is greater than 2, so I can consider that element. Now if I move into the left hand side, I can see that 6 is greater than 2. Okay, nice. and 5 is also greater than 2. Nice, but 1 is smaller than 2. So the nearest minimum element in the left side for 2 will be 1. So I can consider only these two elements for 2. Fine. So the total elements I can consider for 2 will be these 4 elements. So my length will be 4. So my answer for this case will be 8. Now for 3, let's consider what will my length. Okay, for 3, I can say that for 3, there are no elements available in the right hand side, but let's see what are the elements available to me in the left hand side. Okay, 2 is the nearest minimum element for 3 in the left hand side. So that means I have just of length 1 for 3 and answer will be equal to 3. Okay, I have considered all the elements by using that analogy, and I can see that if I want to consider that element, so I can just get the maximum length of 5, maximum length of 2 for 5. So that means it's okay to do like that, and in the end what I can do, I can find the maximum answer out of them, which is 10. So 10 will be my answer. Nice. If I do in that way, I can figure out the answer. Nice. And I can see that 10 is the answer for this question. Nice. So let's try to write a code for this. What will be the simplest code to write the solution for this will be, let's first have a size. Okay, I need two informations for every particular element. What will be the nearest smaller element? For that element in the right hand side, I also need the information, but with the nearest smaller element for that particular element in the left hand side. So I need both the information for any particular element. So let's say I created two vectors. The one of them is storing the smaller in right side. I need that information for all the elements. So I just initialize. I just need the size of n and the what should be the default value. Okay, I know that if for that element I haven't found any element which is lesser than that element in the right hand side, so I can say that okay, let's just say that okay, so in that case I may end of my list, so I can safely mark it as n, okay, because that seems like a good thing. Okay, now I need one more information which is smaller in the left side. I need that information as well. Okay, if I need that information, so I need this information an element, and in similarly I know that if I move into the left side, I haven't found any element which is lesser than this particular element, so I end up with an index of -1 because something like it goes beyond 0 in the left hand side. So I can pick the default value as -1, which seems like a good thing to me. Okay, now let's fill both of these arrays. How we can fill? So this is quite simple. We need a stack for this, because what we need to do, we need to figure out the nearest most element in the right hand side as well as the left hand side. As we discussed in the previous question, we can easily do this by using stack. And let's say I created a stack. Now let's first solve it for the right side. And let's say I need to iterate. Okay, now how we can do that thing? Let's say I consider the edge case. Let's say my stack is empty. Or the value available at the top of my stack is actually less than or equal to my current element. If that is the case, so I haven't found the answer for my current element yet, as well as for any element which are at this stack, because I just found an element which is greater than the element present at the top of the stack. So I need this information. So I need to push that element into the stack. So that's the only thing that I can do. So I am done here. So I can continue. Now, if that is not the case, that means what does this means that I am at the top. Okay, I need to first write the edge case. I need to iterate up till my stack is not empty, and my stack top is, if it is greater than AI, that means the ith element, it's basically lesser than the topmost element. So I can say that for the topmost element, ith element will be my answer. So as I'm moving into the right side, so I can update the answer for smaller right side stack dot. So I can safely update it as I. Now I need not need the information for that particular element, so I can easily safely pop that element from my stack. Nice. So if I do in continue that way, I haven't figured out the answer for I yet, so I need this information. So I need to push that element into the stack. Let's say I just push that element in my stack. Fine. If I do similar way for my left side to populate this array, okay, I just need to apply the similar algorithm for this case as well. So what I can do, I just move into the left side now, and my algorithm will be something like this only. So I can just copy the same algorithm. Okay, so if that is the case, so but instead of left side, now I'm populating my left array for each element. Now, by doing these two operations, we just populated both of my arrays. We now have that information that for each particular element, what will be the nearest smaller element in the right side, as well as we have that information what will be the nearest smaller element for a particular element in the left side. We have both the information. Now, let's calculate the answer. Let's say initialize my answer as 0, because obviously my answer will be bigger than that 0, so I can update my answer for each particular element. Now, okay, what I can do, okay, now what I can do for, let I have an element in consideration, which is element in consideration, let's say it is a of I. Now, what will be my temp answer? That temp answer is basically this answer, which symbolizes that if I take this particular element in consideration, what's the maximum area of rectangle that I can achieve? Okay, let's try to think. Maximum rectangle area that I can achieve for that particular element. Okay, for that, my length will be, height will be this, and what will be my width? I know that if I need to figure out the width, I need to find the nearest smaller element in the right side as well as in the left side. So for this, that's why I just keep the default value as -1 for left hand side and n for right hand side, so that it's easy to compute that thing. So let's say for 2, I have my nearest smaller element in the left side will be -1 and in the right side will be 1. So if I take the whole length will be equal to 3. If I take the whole length, my whole length, that is nearest right side minus of particular that element I, and I take the nearest left side, the particular element I plus 1. So this will be the total length. But in that particular length, I just include the nearest smaller element in the right side as well as for the left side. But I don't need to include these two elements, because these two elements shouldn't be included in the rectangle. So I can safely remove -2 to remove these two elements, and I can update my answer as max of my answer and temp answer. If I do in that way, I can easily achieve my answer and I safely return answer in the end. Let's see. Okay, I just initialize my array and I just keep my smaller right side as n. I just add the default value as n. For the smaller left side, I just did in the similar way. I maintain a stack. Okay, we missed one thing. Okay, what we need to do, because there are many elements, after solving it for the right hand side, for that particular elements, we haven't find any elements in the right side which are smaller than that element. So that element still remain into this stack. So I need to remove all that elements from my stack. So I need to remove, let's say I removed that algorithm from my stack. Okay, so now let's look at the complexity part of it. This is running order of n time, this is running order of n time, and also this is running in order of n time. So the overall complexity will be 3n, which I can safely say it as order of n. Okay, nice. So we just solved this question in order of n time. Nice. That sounds like good thing. Now let's test my thing first. Okay. Let's see the errors. we have an error at 51st line. Okay, I guess the error is okay. It's not nearest. It's smaller. Okay, smaller. And is there anything else? Okay. Okay, this is correct. And you need to push. Okay, now let's test it again. Okay, nice. Okay, everything seems correct to me. Let's submit my code. Let's see. Oh, nice. We solved this question. Nice. So now let's look the other question for today. We have solved both this question. Now let's look into this question. What this question is saying, that we have been given an array of integers. This is a sliding window of size b, which is moving from very left of the array to the very right. And you can see that W numbers in the window. Each time the sliding window moves rightwards by one position, and you have to find the maximum for each window. Okay, so the question is, we have been given an array, and in that given array, we have been given a window. We need to figure out the maximum element in that window, and that window is basically a sliding window. So what does it mean? Let me explain you. That let's say we have been given a window of size 3. So in the starting, let's say we consider the first 3 elements of the window, and we figure out the maximum, and the maximum value for these particular 3 elements obviously will be equal to 3. As you can see that 1, 3 and minus 1, the maximum element for this will be 3. Nice. So now let's look at the other thing. Okay, now for if I just take the other next window for this particular case, the next window will be 3, minus 1 and minus 3. Nice. So if I take this window, and then I can see that the maximum for this window will be equal to 3. Nice. If I take the next other window, then I can say that the maximum for this window, it's equal to 5. Okay. And for this window, if I go in the similar fashion, I can see that, okay, the maximum is 5. And for other window, I can see that the maximum value is 6. If I go in that way, okay, if I take the last window, the maximum value is 7. Okay, so this is my question. How I can solve this question? Okay, let's think. Okay, let me move to here. Now, how we can solve this question? Let's see. Okay, we have been given as some array. Let's say we have been given array. Let's say we take the random array now. 4, 7, 8, 3, 2, 5, and we have been given b as 4. Let's say this is given to us, and we need to figure out the maximum element in each window of length 4. So the first window will be 4, 7, 8, 3. So the maximum value for this window will be equal to 8. Nice. Now the next window will be this, and again the maximum value is 8. Okay, the next window is this, and the maximum value is 8 again. Okay, how I can solve this question? Let me first think. Okay, I need to consider all the windows. So the brute force way will be, I maintain a window and I just keep one start and end, which is referencing my current window, and I just figure out the maximum element in that particular window and I will get an answer. That's the thing that I can do, and I will achieve and I can solve it. But now let's look at the time complexity to solve this question. Okay, if I maintain one window, that means, what does it mean? It means if I need to find the maximum, okay, one way is what I can do. I can just find the maximum by do the iteration from start to end. But this will lead to other order of n time, and how many updation that I need to do for start end, as there are only order of n windows. As we can see that the first window is of 4 element, then the next window of this 4, and the next window of this 4. So there are only 3 windows, and that's of order basically n. So the overall complexity will be order of n square. Can we improve this algorithm? Is there any way to improve this algorithm? Okay, the one way that we can do to improve our algorithm is what I can do. I can maintain some sort of structure that we know, and that will tell me the maximum element within a given range. Within a given range, I can do something like that, and maybe that will solve my question. But if I need to maintain that structure, we already know that the segment tree provides that sort of flexibility that gives us the maximum value in a particular range. Okay, and this will solve my problem in order of n to order of log n. If you can use something like that, but even then my complexity will be n log n. Can I improve further if I want to solve this? Let's see. Maybe we can improve it further. Okay, let's say we have been given an example 4, 7, 8, 3, 2, 5. Okay, what we can do? Okay, what I can see here that, okay, let's say the window size is 3. Let's say the window size is 3 in this question. But I can say that, first of all, let me consider the first 3 elements of this window, which are 4, 7, 8. Okay, I just figured out one thing, that if I have only one element, I can store this information. Now I encountered an element which is greater than that element. If that particular element is greater than that particular element, so I can say that this element won't be the answer in any of the window. Why? Because this, I just found an element which is greater than this element and has a greater index as well. So that means if there is a chance that I will just need to remove an element, that will be the element of lesser index, obviously, for sure. And if I just figure out an element which is greater than this, so that's of greater use than this. So I don't need this information. So I can safely remove this information and I can keep this information only. Now, in the similar way, if I figured out 8, okay, I can remove this information as well in a similar way, and I can just store the information 8 only to solve my answer. Okay, if I do in this way, I can solve this question. Okay, let's see. Now my answer is 8 for this. Now, okay, now let's say I now come at 3. If we figure out an element which is lesser than this element, okay, but I can't say anything now. I can't say anything now because there may be a possibility, because it has a larger index, there may be a possibility that for some other window, this will be my answer. So I need to store this data as well. So that means we are coming up with some algorithm. If we are figuring out an element which is greater than any particular element, if that is the case, so we can safely remove the element which is at the end of my some data structure. And if I figure out an element which is smaller than that element, so I just need to append that element in the end. Nice. But one thing we also need to show that if we go in some other window, we need to remove the elements which are not in that window. And as I am just adding all the elements in the increasing order of index in that data structure, in some data structure, so I can just check whether the first element is of previous window or the current window. If it doesn't belong to the current window, I can safely remove that element. So, okay, so one thing that I'm sure that I need, if I want to solve this question by using this algorithm, I need a data structure which will help me in adding in the end, also removing in the end, and also allows me the ability to remove from the front. Okay, and all those operations should be as efficient as possible if I want to make my algorithm faster. So what data structure that comes to my mind? Okay, can I use stack? If I use stack, then these two operations will perform in a good way, but not this. Okay, so what sort of data structure I can use now? Okay, can I use queue? If I use queue, I can do this operation and this operation, but I need to sacrifice over here. Okay, then what other data structure that I can use? If I'm using some complex data structure, then the complexity will be log of n. And we already know that we just build a segment rather than that data structure that will already solve us our problem in order of log n. So we need some sort of data structure. Okay, one thing that comes to my mind, why don't we use the doubly linked list? In the doubly linked list, we can add, and we have both the pointers, head and tail. We can just add the element, and then we can easily remove the element from the end in order of one time. and add that element in order of one time. And similarly, what we can do this thing in the front as well. If we follow this approach, we make our algorithm efficient. Nice. So in C++, we have this doubly linked list in a form of dequeue. So we can use dequeue in our case and we can solve this question. Nice. So now let's try to look at the example and we'll solve this question again. We have elements 4, 7, 8, 3, 2, 5. Okay, if that is true, now let's try to think. Okay, I have a window of 3 elements. Let's say I maintain a dequeue where if I have a first element, I just put it and I figure out the second element. If it is greater, so 4 is of no use, I can remove that element. So I can put 7, and if of no use, I can remove that element. I can put 8. Now I just end up with the window. What will my answer? It will always be the first element in the dequeue, isn't it? Because the way we are just storing the data, the first element of that window will always give me the answer. So if we do in that way, we can just get the things done, man. That's cool. We can do in that way. Cool. So now if I want to consider a next window, it will be something this. Okay, now let's see what is the index of 8. Index of 8 is 2, but in the current it belongs to the current window, so I not need to remove that element. So what I can do, I can just add 3 here because I need to add 3 because it is lesser than this element and this element can be the answer for other windows. So I need to add 3. Now I am at, okay, I just add 3 and the answer will be again 8. And similarly, if I do it that way, I will find the answer. Now let's try to write the code for this. We figured out everything, what is required, and we just figure out the algorithm to solve this question. Okay, how we will write the code? One thing is clear to you, one thing is clear to us that, okay, let's say first take the size. We need a data structure like dequeue, and let's say it's dequeue. Okay, now I need to iterate over my link, over my array. Okay, let's first do the parts. Let's say first cover the edge cases. If my dequeue is empty, and or if I have an element in the end of my dequeue which is basically greater than my current element, in that case what we need to do, we just figured out in that case we may need this information. So in that case we can add this element in the end and that will help me to solve this question. Now if that is not the case, what we can do, we can check while, okay, my dequeue is not empty and we are getting, okay, we need to add 4 as well. What we can do, if my element in the back, they are lesser or equal to my AI, because I just found an element of greater index and it is greater than the last element of my dequeue. So that means I don't need that last element in my data structure. So I can safely remove that element. Okay, I can do in that way. So in the end, I need that ith element. So I need to add this element in the end. So I am done. But I need to remove all the elements which are not belong to my current window. As we can see that, okay, my next window will start when I becomes greater than or equal to B. So what we need to do in that case, if that is the case, okay, let me first initialize my answer as well. Okay, and so that means if I just end up with an index greater than or equal to B, what does it mean? It means that we just completed our one window. So I can add the answer for that window in my answer vector, which will be the front of my dequeue, as I already discussed why it is, isn't it? So it will be my front. Okay. Now what I can do, if that is the case, now what I need to do, I need to check whether the first element of my data structure is in the current window or not. So for that, first I need to check the base case. If my dequeue is not empty, otherwise it will give us the segmentation fault. And if my dequeue is not empty, and we can say that the element, okay, the index of the element in the front should be, if it is, okay, if it is the first element, it's the 0th element. If I'm at the second window, then the index, if the index is 0, then I can safely remove that element. So the index will be I minus pi, because if I at the next window, my I will be b, and b minus b will be 0. If I'm at the next window, my I will be b plus 1. So if in the front I have the element which is having index 1, so I can safely remove that element. So if I do it that way, I can easily solve this problem. So if I do it that way, what I can do, I need to remove my element from the front. Okay, if I do it that way, I'm done. Nice. But okay, but what about the last element? What about the last element? When I'm at the last element, I haven't updated the answer for my last element. So I need to update it here. Let's say, okay, that will be, my answer will be dequeue dot front. Okay, I just don't need to add the answer dot front. It will be the element for that. So I need A for that case, A for that case as well. If I do in that way, I think this should work. I need maintain dequeue, I maintain vector. When I do in that way, I'm pushing my answer. I'm considering every cases. Now let's test. Oh, I need to return answer as well for sure. In that way. Okay, nice. Correct answer. Now let's submit the code. Nice, we solved this question. Now we are already ahead of our streak. We completed the 2-day streak in a really good way. Okay, nice. So this is all about today's lecture. Thank you guys.